So our goal is to define acids and give examples, and there are two types we're going to talk about. And it's basically the same thing, but looking at it in a different lens. And there's Arrhenius acids and bases, and those are an acid. Those produce H plus ions, and a base is those that produce OH negative. And the Bronsted-Lowry definition is a proton donor, and a base is a proton acceptor. All right, we'll look at it right now. So Arrhenius is a chemical that produces H plus ions in aqueous solutions. So I have a chemical. I put it in here. It dissolves. And now I've got H plus ions in there. All right. Here we have some HCl. When I put this in some water, the HCl breaks apart. All right. And I've got one of these, this one, having an H plus charge or a hydrogen ion. All right. So the equation for that, this is nitric acid, H plus aqueous. All right. And that is what an Arrhenius acid is. And this H plus then can go on to form with water the hydronium ion. All right. I think that is a little more descriptive of what's going on than a random proton just be hanging out in solution. All right. But the definition for the acid, it produces these types of ions. All right. Now the base is a chemical that produces OH negative when dissolved in an aqueous solution. All right. So here's my solution. I've got the OH ions floating around. That came about from taking a chemical and putting it in. All right. Now, these are things like NaOH, LiOH. It's easy to see why these are bases, according to this definition. Anything with hydroxide as an anion. Just like with acids, it's easy to see like HCl, H2SO4, hydrogen bromide. All right, you can see all of these have that H as a cation. That makes them easy to spot as an Arrhenius acid or base. All right, and this would be the equation would be NaOH yields Na plus plus OH negative. AQ, AQ, AQ. All right. Now, Bronsted-Lowry is a definition that came along further or after, and they looked as an acid as a proton donor and a base as a proton H plus being the proton acceptor. And I think this is a little more realistic, in my humble opinion, For example, when you take HCl and well, it wouldn't be in equilibrium because it's a very strong acid. You're going to transfer this proton over to this water molecule, making this the acid and water acting like a base. All right. Now, it isn't a base in the sense of it on its own, it needs the acid to act like a base. But this definition is going to give us a good um, building block to when we move on to conjugate acids and conjugate bases. So, this would be your uh, how a Brown-Sedlowry looks in an equation where you've got your it's donating a proton to a base. All right, and that's why it is an acid. Here's another example of a proton donor. Some metal cations, when they're in solution, they form these complexes like this. Oh, all right, and you've got these bonds here, intermolecular forces. And as this attraction here goes up, the bond between some of these oxygens, or essentially all of them, but we're only going to focus on one. This bond gets weaker, and then what ends up happening is another water molecule will come along, and this whole thing will donate a proton to this water molecule, and then it'll make that a hydronium in the solution. All right, so you'd have Fe plus 3 with bonded with 4 H2Os plus um, H2O, and and this is going to be an equilibrium reaction. This is going to make H3O plus and Fe. I put that in the wrong spot. And this would be Fe 3H2O, and then I'm going to run. I ran out of room. Fe 3H2O OH negative plus, and the whole thing is plus 2 now. It's a 2, not a 3. Right? So that's another example of a proton donor. This definition is a little more encompassing of the different types of acids and bases, or the different chemicals that can be an acid on our base, because sometimes it's not as clear where the proton is coming from. It doesn't always come from this species. It comes from this species tricking water to give a proton to another water molecule. It's a little bit, this definition has a little more chemistry, if you will, involved with it. All right. Now, here is a weak base, NH3, and if we put that with water, oh, what's it going to do? All right. Well, we know that NH3 looks like this, and it's got that trigonal pyramidal shape with these lone pair there. And that lone pair with water is going to attract this hydrogen, a hydrogen. And it's going to form an equilibrium because ammonia is kind of a weak base, and it's going to form this species and this species. All right, so we're set up with, now we make NH4 plus, which is aqueous, and OH negative, aqueous. All right. Now, in this definition, since this accepted a proton from water, this would be my base and this would be my acid, because that's uh, donating a proton. So water can really act as an acid or a base depending upon what it's with. All right, and uh, that is what a Brownstedt-Lowry base is, and what a Brownstedt-Lowry acid is, and Arrhenius acids are, and bases.